SwayamPrabha. Digital India. Educated India.
I welcome you all to the session of thermal engineering basic and applied, and today we shall continue our discussion on the critical pressure ratio, and finally we shall try to discuss about the physical significance of critical pressure ratio essentially in the context of nozzle flow and the design of flow nozzles. So, if we try to recall, in the last class we could establish the expression of critical pressure ratio, and though we did not write the definition of critical pressure ratio, but I have tried to mention that the critical pressure ratio is the ratio of exit pressure to the inlet pressure for which mass flow rate through the nozzle per unit area is maximum. So, if we try to write the expression of mass flow rate through the nozzle per unit area and then the expression of the critical pressure ratio. So, the mass flow rate of steam per unit area m dot by A 2. Why I am writing m dot? Because from continuity we can write m dot 1 equal to m dot 2 equal to m dot. So, this is m dot 2 by A 2, that is equal to under root 2 k by k minus 1 into P 1 rho 1 and P 2 by P 1 power 2 upon k minus P 2 by P 1 power k minus k plus 1 upon k. So, this is the expression of the mass flow rate of steam through the nozzle per unit area. Right, and we also have discussed that to obtain, we also have discussed that mass flow rate of steam per unit area or even multiplied with this A 2, because A 2 is fixed depending on the flow nozzle exit area. What we can see that this expression, this quantity is function of P 1 rho 1 k and also the ratio of P 2 by P 1. So, for the constant P 1 rho 1 and k, the quantity m 2 by A 2, m dot by A 2 is function of P 2 by P 1, right, because that P 1 is also, if we consider that the flow pressure of steam which is entering to the nozzle is constant, density at that particular cross section we can assume it is constant. I mean at that cross section if the density variation is not there and k is also constant, then we can see this quantity is function of P 2 by P 1. In fact, that is what we have discussed in the last class. So, this quantity P 2 by P 1 is the pressure ratio. That is the ratio of exit pressure to the inlet pressure when there is a flow of steam through the nozzle. We also could establish the expression of the critical value of this pressure ratio, which will give the maximum mass flow rate per unit area through the nozzle, and through by doing a simple calculation, we also could write the expression of P2 by P1, I mean critical value, equal to R, and this R equal to P2 by P1 critical equal to 2 upon K plus 1 power K by K minus 1. So, this is the critical value of pressure ratio. So, the critical means this will give maximum mass flow rate through the nozzle. So, this will give maximum mass flow rate through the nozzle. Now, let us discuss today. So, we can see that this is the critical pressure ratio, and which depends on the value of K, that is the index of expansion for the isentropic process. So, when steam is passing through the nozzle, we have assumed that the flow can be modeled by an isentropic process, and following that process we had we had tried to mathematically model the process, and we could recall that K is there, and that K is basically index of expansion for the isentropic process. Okay. Now, the so that means we can write when there is a flow of a compressible fluid through a convergent channel. So, when there is a flow of steam or when there is a compressible flow of fluid through a nozzle, the ratio of exit pressure to the inlet pressure of this nozzle or convergent channel is known as the critical pressure, exit pressure to the inlet pressure of the nozzle, for which the mass flow rate through the channel or nozzle is maximum, that is the critical pressure ratio, and the corresponding exit pressure is known as the critical exit pressure. So, let me write here, when there is a flow or a compressible fluid flows through a convergent channel, within bracket I am writing nozzle, the ratio of exit pressure to the inlet pressure for which the mass flow rate is a maximum, right, is called the critical pressure ratio. Right. So, in fact, this is the critical pressure ratio for which the mass flow rate of stream through the convergent channel or nozzle is a maximum, right. And from this we also can write the corresponding exit pressure is called critical pressure. The corresponding exit pressure is called critical pressure or as the critical pressure. Okay. So, when if there is a convergent channel like this, so this is a convergent channel and there is a compressible flow and we are assuming that there is no heat loss. So, when there is a flow through this convergent duct, we are assuming that the system is not having heat interaction with the surroundings, and if this is the outlet 2 2 and this is the inlet section 1 1 and this is the direction of flow, the pressure ratio P2 by P1 for which the mass flow rate per unit area through the channel should be maximum, and the pressure, the corresponding pressure at the exit pressure is the critical pressure. So, in this case 2 2 is the exit section, 1 1 is the inlet section. So, the corresponding pressure at the exit, that is P2, is the critical pressure. Okay. Now, I would like to discuss a few issues in this context. So, you can see that we have discussed about the critical pressure ratio, that is nothing but the pressure ratio, that is exit pressure to the inlet pressure, right, for which the mass flow rate is maximum. So, that means we are trying to have the maximum mass flow rate, and we can see that mass flow rate will be maximum if the velocity is maximum. So, if we try to go to the next slide, so mass flow rate whether it is at section 1 1 or section 2 2, say we are talking about section 2, that is rho 2 A2 into C2. So, we have tried to find out m dot 2 by A2, that is rho 2 into C2, right. Density will change with a drop in pressure, right. So, that is modeled by that isentropic equation, process equation. So, if you would like to maximize this quantity, we are in process of maximizing this quantity by having a suitable design of the nozzle. Essentially, it indicates that we need to increase the velocity of steam at the exit of the nozzle. So, when you are talking about critical pressure ratio for which mass flow rate is maximum, that means the velocity of steam at the exit of the nozzle is rather becoming maximum. So, velocity of steam at the exit of the nozzle becoming maximum, I mean it indicates that the cross sectional area should be minimum. So, if we try to look at this quantity m dot 2 is equal to m dot 1 equal to m dot. So, let me write m dot 1 equal to m dot 2 equal to m dot. So, this is fixed. Density will definitely fall, density will definitely vary with a change in pressure, but if you would like to maximize this quantity, C2 has to increase. Since this quantity is fixed, now if we need to increase C2, definitely A2 should reduce. So, since m dot 2 is fixed, that we can see from this quantity, because we cannot compromise with the mass flow rate. Our objective is to get higher C2, because if we need to have it, then A2 will drop, because objective is to get maximum mass flow rate. So, basically when the nozzle is operated at this particular condition, that is at this critical pressure condition, and when the pressure at the exit of the nozzle is critical pressure, can't we say something else. So, let me write here. So, that means we can say, so basically it is the pressure at which the area is minimum and discharge per unit area is a maximum, right. So, it is the pressure at which area is minimum and mass flow rate per unit area is maximum, and that pressure is the critical pressure. So, critical pressure is the pressure at which area is minimum and discharge per unit area is maximum. So, this is basically and the smallest cross section cross sectional area of the convergent channel is known as throat, as the throat. So, basically just we are trying to look at it from different perspective from this simple mathematical expression that the critical pressure we have discussed that the corresponding pressure is critical pressure. So, our nozzle is said to be operating or said to be at the critical pressure condition when the mass flow rate is maximum and area is minimum, because if we need to have mass flow rate is maximum, we have seen the velocity should be maximum. To obtain the higher velocity, the area should be reduced. So, area should be minimum. That means, this is the section where the pressure is critical pressure, area is minimum, and that is known as the throat of the convergent channel or nozzle. Okay. So, this is very important. That means, you should keep in mind that critical pressure is the pressure at which area is minimum and that minimum area of that particular convergent channel is known as the throat. Okay. Now, let us quickly see rather if we write the expression of mass flow rate per unit area. That is 2 k by k minus 1 P1 into rho 1 P2 by P1 power 2 upon k minus P2 by P1 power k plus 1 upon k power total power half. So, this is the expression of mass flow rate. Now, this is the mathematical expression of the mass flow rate per unit area. If we try to plot, the mass flow rate, so say this is m dot, that is mass flow rate, right, and this is P2 by P1. Why? If we go back, we have written that m dot by A2 is function of P2 by P1. So, let us try to have the graphical plot of the graphical representation of this function m dot by a2, which is the function of p2 by p1. What we can see from this expression? So, when p2 equal to p1, right. So, that means I will be discussing 3 different cases. So, case when p2 equal to p1, this means p2 by p1 equal to 1. So, if we scale it from 0 to 1, say this is 0, this is p2 by p1 equal to 1. So, this is p2 by p1 equal to 1. So, when p2 by p1 equal to 1, we can see from this expression that mass flow rate is 0. So, it will start from here. So, this is 0, right. Now, when p2 by p1, that is p2 equal to 0, this means p2 by p1 equal to 0. You have studied in fluid mechanics that there will not be any flow until and unless we are having the driving pressure difference. So, maybe even if we look at this particular cross section, so this is p2 and this is p1. So, the driving pressure difference is delta p, that is p2 minus p1, right. So, or p1 minus delta p, p1 minus p2. So, if the pressure at exit equal to 0, there will not be any flow. If there is no flow, we cannot think even to have mass flow rate. So, it will be 0. So, this is the point when p2 by p1 equal to 0. So, that means we can see that mass flow rate is equal to 0 and somewhere at the critical mass flow rate p2 by p1, it will be maximum. So, when p2 by p1 equal to p2 by p1 critical, m dot by a2 is maximum. So, that means somewhere we will be getting maximum value right. So, try to look at why the curve will have trend towards left. If we keep on so when P2 equal to 0, there is no flow, right. So, these two pressures, I mean you need to reduce the pressure. So, when P2 equal to P1, there is also no flow. When P2 equal to 0, that we can see from the mathematical expression, that m dot by A2 equal to 0. So, if we try to go here, that P2 should not be equal to P1. If P2 is less than equal to P1, then only there will be flow, right. So, when P2 equal to 0, then ideally we are supposed to get maximum flow rate, because if P2 reduces, then it will have, we will be having driving pressure difference. So, when P2 is becoming 0, we are supposed to get maximum mass flow rate, but if we look at the mathematical expression, when P2 equal to 0, mass flow rate will be equal to 0. So, let us now plot it. I will explain the physical issues later, right. So, this is the, if we give the name, say this is point A, this is point B and this is point C. So, A, B, C, that is the theoretical curve. The curve ABC that we have drawn now, it is the theoretical curve. Okay. So, now try to understand that reaching at the maximum value, if we further reduce P2 and if we make P2 equal to 0, though we are supposed to get maximum flow rate, but following this mathematical expression we can see that the mass flow rate should be equal to 0, but this is not the case, that we will explain this. So, before going to this particular aspect, though it is mathematically 0, that we can deny if we look at the mathematical expression, but you all have understood that if we reduce, so that means we are bringing the ratio of P2 by P1 from 1 to the closer to 0. So, if we reduce P2, then we are having more pressure difference, so we are supposed to get more flow rate, but that is not, we can see that is not the case, that we can see from this curve, which is verified by this mathematical expression as well. So, before going to discuss that particular part, to figure out what is there, let us now look into the physical significance of the critical pressure ratio. So, now let us look at the physical significance of critical pressure ratio. So, if we start our equation from that particular equation, that is dP by rho plus CdC equal to 0, right. That equation we are getting from CdC plus dH equal to 0, and we are using the value of dH, rather we are substituting the value of dH by dP by rho from the state property relation, TdS is equal to dH minus VdP. For an isentropic process, dS equal to 0, so we can write dH equal to VdP, that is dP by rho. Now, in this equation, so basically what you can write, we can write integral C1 to C2 CdC equal to minus P1 to P2 dP by rho. To have the closure, we need to invoke the property relation, that is we are using P by rho 1 to the P1 by is equal to constant equal to P2 by rho 2 power k, right. So, what we can do here, we can write, so that means we can write this is nothing but constant power 1 upon k into P2 by P2 to P1 dP by P power 1 upon k. So, that is straightforward. So, from here we can write that P by rho power k equal to constant, right. So, we are using it, we can quickly go further step. So, if we perform that integration, we can write that C1 to C2 CdC equal to, we can write constant power 1 upon k into k by k minus 1, and then we can write that P power minus 1 upon k, and that already you have taken into account. So, basically we can write this is P1 k minus 1 upon k minus P2 power k minus 1 upon k, right. What we can do next is k by k minus 1, we can take this constant power 1 upon k inside, and this constant power 1 upon k we can write this is P1 into V1 power to the power k, right, power 1 upon k into P1 to the power k minus 1 upon k, and the same constant power 1 upon k we can write like P2 into V2 power k to the power 1 upon k into P2. So, this is P2 power k minus 1 upon k, right. So, basically we have to do some algebraic manipulation. What we can write? So, see this is nothing but k by k minus 1 and this is coming as P1 into V1. So, P1 into V1 minus P2 into V2. So, this V1 and V2 are the specific volume at section 1 and section 2 respectively of the stream that is flowing. So, this this is very easy. What we can do further is we can write this, we can take P2 V2 outside. So, K by K minus 1 P2 V2, and we can write P1 V1 divided by P2 V2 minus 1, right. So, you can understand that we also can write this like this, K by K minus 1 P2 into V2, and this is P1 by P2 into V1 by V2. So, since P1 V1 to the power k equal to P2 V2 to the power k, therefore, we can write V1 by V2 should be equal to P2 by P1 to the power 1 upon k, right. So, if we write here that P1 into P1 by P2 into P1 by P2 power 1 upon k minus 1. So, this is 1 upon k. So, if we go to the next slide, we can write that integral C1 to C2 CdC equal to k by k minus 1 P2 V2, and this is P1 by P2 power here it is P2. Sorry, I have done one small mistake here. It should be P2 by P1. You can see this is P2 by P1. So, it should be P2 by P1. So, just it is P. So, you know that we can write this is P1 by P2 into minus 1 upon k. So, if we do this P2 into P1 by P2, or we can write straight away. So, this is 1 minus k minus 1 upon k, or that is basically we can write 1 minus k upon k minus 1. So, this is the expression. So, what we can write here is that C2 square minus C1 square by 2 equal to k minus k by k minus 1 into P2 V2, and this is P1 by P2, or we can write sorry, this is again not 1, we are trying to write it P2. Why we are trying to write in terms of P2, I hope you have understood, because we need to relate it with the critical pressure ratio. So, P2 by P1 to the power 1 minus k by k minus 1. So, we are trying to have the expression of C2 in terms of the critical pressure ratio. Till now we have discussed about the critical pressure ratio and mass flow rate. So, it is the critical pressure ratio, it is the pressure ratio at which area is minimum and mass flow rate per unit area is maximum, right, and the corresponding pressure at the exit is the critical pressure. So, now we would like to know what is the expression of critical velocity in terms of the critical pressure ratio, right. So, we can have similar argument. See, that if it is the channel, if it is the convergent channel, and this is the cross sectional area 1 1, this is the cross sectional area 2 2, and what we can see that C2 or C1 is much less than C2, because area at 1 1 is much higher than the area at 2 2. So, definitely C2 would be maximum, and that is what the objective is of having this convergent nozzle. So, what we can write? We can write C2 square by 2 equal to, we can have k by k minus 1 P2 V2 and this P2 by P1 power 1 minus k by k minus 1, right. So, what would be C2? Now, when P2 by P1 is equal to P2 by P1 P2 by P1 critical, then C2 also will be critical. So, let me write over here, when P2 by P1 equal to P2 by P1 critical, then C2 will be equal to C2 critical. So, what is the value of C2 critical? So, that means C2 critical equal to 2k by k minus 1 into P2 V2, right, into we know that P2 by P1 2 by k plus 1 to the power k by k minus 1 into 1 minus k by k minus 1. So, basically this is the equal to, I mean not nearly equal to, this is basically P2 by P1 critical. So, what we are doing, we are putting the value of P2 by P1 critical over there, and if we do one step further, we can write this is nothing but 2k by k minus 1 into P2 V2, and this is basically minus. So, k minus k plus 1 upon 2 minus 1. So, that means this is coming k plus 1 upon 2 minus 1. So, that is nothing but 2k by k minus 1 P2 V2, and this is k minus 1 upon 2. Okay. So, basically you try to understand, we are getting, so this is C2 critical square. So, we can write now C2 critical equal to under root k P2 into V2. What is k P2 into V2? So, this is the sonic velocity at the exit. So, that is basically the sonic velocity at the exit. So, basically we can write equal to corresponding acoustic velocity. Right. So, when from this particular mathematical exercise we can discuss that when exit pressure is the critical pressure, rather the ratio of exit pressure to the inlet pressure is the critical pressure ratio, the corresponding velocity at the exit of the nozzle, that is the critical velocity, is the sonic velocity, right. So, now let me tell you, so when the exit pressure is the corresponding critical pressure of the nozzle, exit pressure is the corresponding critical pressure of the nozzle, exit velocity also is the critical velocity, that is nothing but the acoustic velocity at the same temperature and pressure of the flow. Okay. So, this is very important. So, now if we go back to the particular expression, what we had mentioned. So, when the pressure ratio is reached at the critical pressure ratio, we have mentioned that when the pressure ratio has reached the critical pressure ratio, flow rate per unit area is maximum and the corresponding exit pressure is the critical pressure, we have agreed upon. Now, from this mathematical exercise, we have established that when the pressure is the exit pressure, corresponding exit velocity is the critical velocity, which is nothing but the sonic velocity of the flow at the same temperature and pressure of the medium when there is a flow. So, now question is, you have seen, if we go to this particular slide, so when the velocity at the exit is the sonic velocity, let me tell you one thing, very important thing, when the velocity at the exit of the nozzle is the sonic velocity. So, when the velocity C2 is C2 critical equal to sonic velocity of the media, So, if you reduce further pressure, that pressure is to be sensed by the exit by the inlet section of the nozzle. So, when the pressure ratio is critical pressure ratio, exit pressure is the critical pressure, and from the last expression we have seen that the velocity is also the sonic velocity, critical velocity, that is the sonic velocity. So, when that is sonic velocity, if we try to reduce the pressure further at the exit of the nozzle, that information is to be sensed by the inlet section of the nozzle to increase the mass flow rate. Question is, whenever there is a reduction in pressure, that means the nozzle is operating at the critical pressure ratio. If we try to have further reduction in pressure, that pressure wave should be the pressure wave should move to the inlet section. That means that information should be sensed by the inlet section of the nozzle. That indicates that a further reduction in pressure, that pressure wave should move to the inlet section, because inlet section should know that there is a further reduction in pressure at the exit section of the nozzle. When a pressure wave is moving through an elastic media, that moves with a sonic velocity. Now, the question is, if the flow velocity itself is the sonic velocity, so a further reduction in pressure, that wave will not be able to reach at the inlet section of the nozzle. So, and at that case, what will happen, the flow rate, whatever we have seen, it will remain constant. So, this is the m dot maximum. So, this is m dot maximum. So, this point at B, which is basically this point is P2 by P1 critical, right. So, a nozzle has reached at the critical condition, a further reduction in pressure at the exit, which needs to be sensed by the inlet section to increase the flow rate, but that information will not be, has to be carried through the medium itself. But since the nozzle exit velocity is the sonic velocity that we have established few minutes back, that further reduction in pressure, that information will not be reached at the inlet section of the nozzle to increase the flow rate, and as a result the mass flow rate will remain constant, and this is the experimentally measured data. So, this is A B and I am writing D. So, this A B D, so this is experimental curve. So, this is experimental curve. So, try to understand, though we have seen that mathematically if I reduce pressure further beyond the critical pressure, so this is the critical pressure ratio and the corresponding pressure is the critical pressure. If we reduce pressure at the exit beyond the critical pressure, mathematically we can see that the mass flow rate should be equal to 0, but the physics is that further reduction in pressure, that information should be sensed by the inlet section, and to get that information a pressure wave should move through the elastic media with a sonic velocity, but already the velocity is sonic velocity. So, that information will not be sensed by the inlet section, as a result of which the mass flow rate will remain constant, and that is the experimentally observed phenomenon. So, very important part is, I would like to write 2-3 important points now. Let me write over here is that, so what we can write is, for a given inlet and exit pressure of a nozzle and a required mass flow rate, the nozzle designer has to evaluate the critical pressure first. Critical pressure at first if the exit pressure is less than the critical pressure, nozzle will be of convergent divergent type. Nozzle will be of convergent divergent type. If the exit pressure is equal to or above the critical pressure is equal or greater than the critical pressure, right, the nozzle will be of convergent type. So, this is very important. So, this is the conclusion of this analysis, that when exit pressure, so whenever someone is designing the nozzle for a given inlet and exit pressure and the mass flow rate, required mass flow rate, designer should first calculate the critical pressure ratio. If the exit pressure is less than the critical pressure ratio, then the type of the nozzle should be the convergent divergent type. If the exit pressure is equal or greater than the critical pressure ratio, then it should be the convergent type. One important thing is, so what we can say, again let me tell you that when the pressure is the critical pressure ratio, mass flow rate through the nozzle is maximum, that we have established, and at that condition a nozzle is said to be choked. So, when the nozzle is operating at the critical pressure ratio, exit pressure is the critical pressure, velocity of steam at the exit is the sonic velocity. At that condition, mass flow rate through the nozzle is maximum and the nozzle is said to be choked. So, this is very important. This is very important question. When a nozzle is said to be choked, a nozzle is said to be choked when the exit pressure of the nozzle is the critical pressure, the maximum mass flow rate through the nozzle is obtained or achieved, and the nozzle is said to be choked. So, we have, if we try to summarize, we have discussed about the critical significance of the mass flow, critical significance of the physical significance of the critical pressure ratio. From there, mathematically we have seen that although if we further reduce the pressure below the critical pressure at the exit of the nozzle, mathematically mass flow rate is becoming 0, but in experimental observation it is seen that the mass flow rate remains constant, and the underlying physics we have tried to explain from the sonic velocity that is reached when the nozzle is operating at the critical pressure ratio. So, with this I stop here today, and in the next class we shall try to solve one numerical problem on the flow analysis of the nozzle. Thank you.